afternoon, everyone. So our third presentation this afternoon is going to be about cooling tower filtration. And I added to the rest of the title, to improve efficiency, tower efficiency, while conserving water and chemical use. And you notice that the water treatment guy just left. I love it. But anyway, why do I know all this? Done it. So anyway, our speaker is going to be David Lamarre. David's with Exel Systems. David's been in the mechanical design and construction industry since 2006. After receiving his Bachelor of Science degree in mechanical engineering from the University of Alberta. I won't mention that's in Edmonton. David moved to Vancouver, very good, and joined Hakon. Oh wow. Yeah, and as an applications engineer, I bet you that was pretty cool. And in 2014, David joined Exel Systems in an outside sales engineer role. So I guess I've known you for a little while. A little while, yeah.
7 8 years.
And some of the other folks over there. So anyway, I'll leave you to it. Again, this presentation is being recorded, and it will be on our the Building Operator Association of Canada website, www.boacalgary.com, and the link will be in there, and also on our YouTube channel, which is under Building Operators Association of Canada. So easy to find. So anyway, take it away, Dave.
Thank you very much, Mark. As Mark mentioned, here's my bio. Went to the University of Alberta, worked for Hakon for a number of years as an application engineer, as Mark mentioned, and over there I designed custom air handlers. From there, moved over to Exel Systems, and I've been with them since 2014, working on cooling towers, cooling tower filtration, and the like. So I will get going here. Now, a little bit about Exel Systems. We were established in 1993. We specialize in the engineering, design, and supply of custom, high-quality HVAC equipment. We represent a number of manufacturers, and the best way to get that information is to head to our website, which is www.excelsystems.ca. From there, we have a complete line card where you can see which is up to date with the various manufacturers that we bring on board as new technology and new manufacturers come around. So a little bit about today. I'm going to be speaking mainly about Lakos centrifugal separators. I've got a demo here that we'll go through at the end of the presentation. And I'm going to be chatting a little bit about how we can apply the centrifugal separators to your cooling tower systems to gain efficiency and basically save you and the building owners money. And I apologize for being rude and checking my phone here, but I am expecting a baby any day now, so if my wife calls, I will run, and my esteemed colleagues here will take over for me. So in cooling towers, I'm going to discuss 4 main points. Basically how solids get into the cooling towers, talk to you about the importance of recovering those solids, and just bear with me 2 seconds here. My computer is off to the side and I need that for my presentation here. We can talk about how clean is clean enough and applying filtration to your systems and how best to apply those methods. So cooling towers themselves are designed to operate in their most as efficiently as possible. And as you operate those towers, they do end up accumulating dirt and debris inside the system, which decreases your efficiency and costs you money, essentially. And a cooling tower, no matter the type, brand, make, model, they all operate very similarly. they are essentially a large air scrubber. The cooling towers pass air over top of a fill media, and at the same time there is water that's passed over that fill media, and through latent heat of evaporization, your cooling tower evaporates a small amount of water and cools the condenser water that's flowing through it. That's how you achieve your cooling, and then pass that condenser water down into your cooling tower or into your chiller. Now, as it's operating, when the air comes in contact with your water, your cooling tower becomes a large air scrubber. So any dirt, debris, bugs, cotton fluff, poplar fluff, all of that will get washed out of the fluid and will collect down into the cooling tower basin. Now, once it collects down in the cooling tower basin, it then gets carried on to your chillers, be it chillers, heat exchangers, anything downstream of your cooling tower. That dirt and debris will get carried down. And there are a few different sources of that debris. One is the air that gets cleaned as it goes through your cooling tower and drops dirt out into your system. The other is from your water supply. So based in Calgary here, we have very hard water. So as your water enters the cooling tower, either through the cycles of concentration through your cooling tower or through chemical induction, a lot of those chemicals will get turned from a suspended solid into cooling tower debris down at the bottom of your basin. So it'll come out of suspension into, out of solution and into suspension. Through your evaporization as well as your makeup water, you will get additional material that comes into your cooling tower and into your systems. So once that dirt, debris, and typically your calcium carbonate from the hard water gets into your system, where does it go? After it enters the cooling tower, it will settle down at the bottom of your basin, and then from there it'll get sucked into your condenser water pump and filter through your heat exchangers, your chiller barrels, and anything downstream of your cooling tower. So that's where we get your chilled water tubes will end up plugging and fouling, as well as your heat exchangers. And here, if we have hard water in Calgary, that will also exacerbate the issues in your heat exchangers. So today I'll talk about the 4 problems that typically occur by the accumulation of solids in your cooling tower. That's corrosion, scale buildup, fouling, and biological activity inside your cooling tower. So biological growth happens very easily out here. The cooling tower is a warm, moist environment, so as dirt and debris build up in your system, it acts as nutrients for any kind of bacteria or growth inside your cooling towers, and it'll actually reduce the efficiency of your chemical treatment that's in your cooling tower. So as that dirt and debris builds up, it can encapsulate bacteria, and that allows the bacteria to form essentially a biofilm. So that biofilm will act as a layer of protectant over top of the bacteria, which then goes to town on your equipment. And no matter how much chemical you add to your system, that chemical won't be able to penetrate and kill the bacteria because it's basically protected by a blanket of dirt. Scale is the next issue that occurs. So scale is when calcium carbonate in your makeup water will come from solution into suspension and actually played out on your heat exchanger surfaces. So be it the cooling tower surfaces, which we see here, this film media here is where we see scale buildup, or inside of your air handlers, heat exchangers, etc. That calcium carbonate will come out and then plate as a hard mineral, and that ends up reducing the efficiency of your system, and your cooling tower and your chiller will have to work harder in order to maintain the same amount of cooling for your overall system. Here we see an example of under-deposit corrosion, as well as a cooling tower basin here with a large amount of rust due to the dirt and debris that's built up in the system. So as I mentioned, there is the biofilm that can occur, and you also get something called a sulfate-reducing bacteria that can occur inside your cooling tower and cooling tower basins. That's when the dirt and debris builds up inside the cooling tower, and it allows bacteria, which is called the sulfate-reducing bacteria, or SRB, it allows it to run unchecked, and what it does is it actually reduces the hydrogen from water into a sulfuric acid, an H2S, and that will pit and eat out the bottom of your cooling towers, and that's called, right here we have under deposit corrosion is what they call it. So it pits the material, and then eventually this corrosion will actually eat through the material and it'll cause leaks inside your cooling tower. So that's one other reason why we want to try and get rid of this material, so that your water treatment is actually able to get to that bacteria and kill it off. So here we have an example of an enhanced tube inside of a chiller. So this is a great spot for your dirt debris to build up on. The enhanced tube has rifles or grooves inside the tube, and it enhances heat transfer in that tube, but it also allows an area for dirt and debris to build up, and it's an area which is prone to that SRB, or sulfate reducing bacteria. And because of that, it will eat through the tubes, and it's not something you can easily see, and it'll reduce both the lifespan of your equipment as well as the efficiency of that equipment as well. So the next thing we'll talk about is fouling. Fouling is when there's a buildup of material on your heat exchanger surface that reduces the efficiency of that equipment. And here on the slides what we're looking at is the end of a chiller barrel, where we see dirt and debris over here on the right, as well as mud or calcium carbonate buildup on the left. And this is the main reason why once a year you typically open up your end of your chiller barrel, drain your chiller, and have to punch out your chiller tubes to clean the system, so it gets rid of all that dirt and debris that builds up. Plate and frame heat exchangers are also prone to the same effects. If you have a brazed plate heat exchanger, it's even more exacerbated, because you can't take that heat exchanger apart. Hence the name brazed plate. All of those plates are brazed together, and you can't actually pull it apart to clean it. So that becomes a great area of concern inside some systems. So I did a small calculation for you guys here to show you an example of how that fouling can actually affect your cooling tower system. And here we see, if we take a look at the table on the left, we show your typical fouling factors on the left-hand column here, and what that equates to in terms of an approximate scale of the thickness of debris that's built up in your chiller barrel. So the typical fouling runs between 0.1, and 0.4, and if we go with an average of a 0.002 fouling factor, that equals 24 1,000ths of an inch of material that's built up. So about the approximate thickness of a human hair, maybe 2 hairs thick inside your chiller barrel. That equates to a 22% increase in power required to run your chiller. And with a chiller being the main heart of your mechanical system, that equates to a whole lot of energy over the course of a year. So if we average out the operation cost of a chiller to be about $125,000 a year, and this is just energy cost, not taking into account chemical treatment or any maintenance or downtime required for cleaning. That 22% equates to about $27,000 a year in additional cost, just by adding that 24,000th of an inch of debris on your chiller barrels. So it's a lot of money for a little bit of slime. Now, how can we increase the efficiency of your system and reduce that load on the chiller and the fouling? Well, the biggest thing is to remove that dirt from your cooling tower. Now, from the charts here, we show 4 different methods, and how the methods of elimination from your cooling tower, so how we can pull that dirt and debris out of the cooling tower. On the upper left, we show no filtration, and from certain calculations through ASHRAE handbook, you can estimate that a typical chilled water system will actually allow for about 3,000 pounds of dirt to be washed out of the air over the course of a year. Now we can go in and manually clean that, and here we show it once every quarter, so every 90 days, so every 3 months. It's a good method. You go in, you get everything removed, but then it doesn't solve any issues whatsoever. That problem just keeps recurring. Every 90 days you have that buildup of material. We can add side stream filtration, which a lot of people like to do. It's an inexpensive, fairly easy method to add a little bit of filtration to your system. But then again, the buildup of material is quite substantial. I mean, you're talking 2% side stream. So on the side stream filters, you can only filter out the debris that you are able to pass through the filter. So at a large system, when you have 2% of your flow going through it, you're seeing a very minimal amount of debris and dirt that are actually being filtered out. Now on the bottom right, we see filtration with a cooling tower basin cleaning system. So this is through the use of what we call a sweeper system. So it's a set of PVC pipes that provide clean pressurized water to nozzles inside your cooling tower. And those nozzles are designed to impart a flow in your cooling tower basin. So as you provide 1 GPM of clean water to that nozzle, it actually imparts 3 GPM of additional flow in or around that nozzle through a Venturi effect. So you essentially get, it's a 4 to 1. So for every GPM you provide, you get essentially 4 GPM of induced flow in total to push that media or that material through your basin out to a drain. And in this case, we show the drain just over here. So we're pushing that dirt debris away from your condenser water drain, which is located on the opposite side of the cooling tower basin, so that you can pull that dirt and debris out, filter it, get rid of it, and then provide clean water back to your cooling tower basin. So in this method, there is still some manual cleaning required once a year. Here we probably have about 500 tons of dirt that'll build up inside the tower. But that typically occurs kind of in the corners and in different areas if your sweeper system is not optimized. You will still have to go back in there every once in a while to manually clean it out. But it does result in about an 80% reduction in debris buildup in your cooling tower, which corresponds to an 80% reduction in dirt and debris that's passed down into your condenser, your chiller, heat exchangers, etc. So why would we recommend continuously removing the media or the dirt? So here we show a typical operation for a 200-ton system. You can get over 4,000 pounds, over 2,500 pounds of dirt and debris that can accumulate every 6 months. That's about ½ a pound of solids per hour. So that's a lot of dirt and debris. And as you continuously filter that out, that'll keep that from getting into your system. So even from the ASHRAE handbook, ASHRAE allows you to use mechanical filtration to help reduce the amount of solids in your system. And that is, they do have a large calculation in there that provides data on a typical 200-ton system, which is where I've pulled all of the data from in terms of the amount of debris and whatnot that's pulled out of your system. So why would we want to add this into your system besides the obvious of reducing your energy costs? This helps maintain the efficiency of the condenser and cooling tower water. It extends the life of your equipment and actually reduces the maintenance and downtime required for your cooling tower and your chillers. And it retains valuable liquid. So as we'll see here in a few slides, the systems that we're recommending they're actually a zero water loss option for filtration. So they don't actually discharge any additional water. They operate with your system and they help reduce the amount of water that you need to dump down the drain. So on a standard system without filtration, you would need to blow down quite a bit of water in order to add fresh makeup and add clean water into your system. Now this will actually dump chemicals down the drain, which you're paying to put into your cooling tower to keep it clean. So it helps basically on an additional level of saving you some money in terms of operating cost in regards to your chemicals. So there's a few different ways that we can apply the filtration to your cooling tower systems. On the upper left, we show the basin cleaning, which I've talked about. So we've got a representation of a cooling tower here, a cooling tower cold water basin, and your system pump. And as I mentioned, we want to try and push that dirt and debris out and away from your system drain, out to a drain which goes to your filtration system, and that will filter the water and bring it back into your cooling tower, so we're not actually wasting any water. We can operate in a side stream cleaning method. Now this will take a portion of your flow, it'll divert it from the main piping, pass it through the filter, and then inject it back into your system. This is typically only recommended if you don't have access to a large enough space to be able to put a full filtration basin sweeper into your system. So if you don't have access into the cooling tower, if there's not enough floor space, or if you just need a very economical solution where you're looking to downsize the cost of the equipment. And full stream cleaning here is the most effective method, but it does cost the most because the equipment itself has to be designed for the full flow of your cooling tower. And it also eats up pump power. You do need to size a pump that will be able to handle the extra pressure drop going through your centrifugal separator. So it has the largest cost, but it does have the biggest benefit because you are filtering 100% of your flow. You're able to capture all of that dirt and debris as it comes through your filter. So as I mentioned before, cooling tower basin cleaning, or using sweeper systems, is our recommended method for any new construction or any existing systems that need to be retrofitted to add something to them. It helps remove solids from your cooling tower, and the nozzles that we add to the cooling tower basin will actually sweep and push the dirt around the basin and push it towards a system drain where it's pulled towards your filtration system itself. So it helps keep it away from your chilled water loop. It does help reduce maintenance and downtime inside your cooling tower. As previously mentioned, it gets about 80% of the dirt and debris out of your cooling tower, so it reduces the amount of time once or twice a year where you have to go in and clean out your cooling tower. Here we show how this is typically done. So we've got our Lakos system sized to feed water to your basin sweeper system. And in order to size these, it's a fairly simple calculation. We use 1 GPM per square foot of a basin area. So very easy to size these systems and provide a rough estimate as to what the flow you need for your cooling tower. If we're filtering a remote sump system, so a lot of places in Calgary that operate throughout the year, they will have remote sumps located in the mechanical rooms, and that helps freeze up, allows you to run your cooling tower all year round without any issues in the cooling tower. In those applications, usually the water level is greater than 1.5 feet, and there we recommend 1.5 GPM per square foot of area. That additional flow allows you to circulate the water that's inside that remote sump and pull all the dirt debris out and capture that debris. If you have multiple cooling towers in your system, we do have economical solutions. So in order to save a little bit of money, we can provide one cooling tower filtration skid along with diverting valves, which are shown here in the diagram. And what this system will do is actually, through the programmable controller, it will filter out cooling tower 1 and cooling tower 2, or A and B, however you have them designated, in certain intervals. So typically we recommend having the filter operate anytime the condenser water pump is in operation. So we tie in our Lakos system to a dry contact with the condenser water pump, and anytime that's turned on, we recommend turning on your Lakos system. That will activate a timer inside the control panel, and based on your requirements and needs for the facility, that timer will actually alternate the filtering from one cooling tower to the next through those diverting valves. So instead of having two separate systems or one system that's sized for both cooling tower basins, we can cut the Lakos system flow in half and then operate one system for both towers. So in the side stream application here, as I mentioned before, it's a more economical option, and we see this quite often in downtown Calgary here, where we have older systems where we can't get the filter located beside the cooling towers or adjacent to them. So this type of system you can put anywhere in the building where you have access to the condenser water loop, so long as it's downstream of the pump. You want to make sure it is not upstream of the pump where you have our system fighting against the system pump for the flow. So we always want to make sure it's downstream of the system pump. And we size these systems for anywhere between 10 and 25% of the overall flow. Anything less is similar to putting a Band-Aid on a gunshot wound. You're not going to get much bang for your buck, so to speak, if you size it for anything less than the 10%. And one thing that people don't actually think about when they're thinking about Lakos filtration is using it in a closed loop system. So the way a Lakos centrifugal separator operates, and I'll get to that in a few slides here, it can filter out any dirt and debris that is 2.5 times the specific gravity of the fluid it's filtering. So these filters can be used for water, glycol, be it propylene or ethylene. They can be used for oils. So they're often used in chip factories or different cooking facilities. So anywhere you've got a particle that is heavier than the fluid you're filtering, you can use that centrifugal action to pull that media or that dirt and debris, whatever it is, out of your system fluid. So in older closed loop systems, anytime you open up that system to do some maintenance, you're introducing some dirt and debris from the fittings. If the plumber doesn't clean the pipe well enough during the initial fill, there will be some other dirt and debris that gets introduced into there. And over time, if your glycol is not maintained properly, you can actually end up with some corrosion byproducts that will build up in the system, and then that'll end up clogging your heat exchangers, your heat pumps, whatever you have on that closed loop system where you don't want to introduce any debris. It'll get in there and clog those systems up. So once again, we do a 5 to 10% side stream application, and because this is a closed loop system, we can get away with a smaller flow through that filter. It's a continuous flow through that system, so even if your system is shut down, we recommend leaving the Lakos filter on. And through our zero water loss option with solid recovery vessel and some other accessories that I'll talk about, it's not open to the system, so you're not just dumping glycol down the drain or wasting money, so to speak, with your filtration system. Full stream, as I mentioned before, it will filter out 100% of the flow, but it is the most costly method of filtration because you need to upsize your pump, and the system equipment is quite a bit larger to handle that full flow. But it does filter out 100% of your flow, so it is more effective.
So would you recommend putting your bleed off that on a cooling tower? I've been running into applications, I always recommend that type of filtration, that's where they put their bleed.
So
just less bleed off, but I'm starting to find a lot of applications it's not. It's actually playing with the pressures in the system.
yeah, so if we use our zero water loss option, which what it does is the filter itself, let's see if I've got a slide here, I wasn't too far away from showing it here. So what we do is provide what we call a solid recovery vessel, which it's just either an 18-inch tall or a 33-inch tall stainless steel cylinder. As the dirt and debris gets filtered out, we plumb the bottom of the filter to the inlet of this solid recovery vessel. That pulls the dirt and debris and a little bit of fluid up into the solid recovery vessel, where we have a fine mesh sock that filters out that dirt and debris, and the fluid itself is pulled from the bottom back to the suction side of the pump. So you end up with a slight amount of circulation through the system, but you're not dumping it down the drain.
So you're not flushing that?
So we're not flushing any water down the drain, so I don't like to double up on your flushing.
Water loss, yeah.
Water loss. So there are applications where instead of this SRV, some people like to put an actuated ball valve.
Mm-hmm.
But then again, we're fighting against the water treatment system because that ball valve will open and flush water at a given interval.
That's the system that I have, and unfortunately it's on 2 towers with the main head, and it's causing nothing but havoc all the time. So I was thinking about plumbing in the bleed onto that, but perhaps this is a better option.
Yeah, you can get these solid recovery vessels, or just small tanks, with the appropriate valves and piping that you can add those to a system that's existing.
Oh.
Like I said, as the filter itself filters out the dirt and debris, that all settles down at the bottom, and it essentially gets sucked out into there. So instead of being dumped down the drain through that ball valve, it just gets continued filtered through there.
Versus.
Oh, did you? Yeah.
It worked really good. Put
Did
it
it?
down on the second floor,
Yeah.
because we had no room.
Yeah, exactly. Yeah, that was.
But we
true.
left the bleed on the tower and it worked great.
Yeah.
So yeah, what I recommend is doing this with the SRV and then leaving the chemical treatment to monitor the conductivity, control the blowdown, control the makeup, the chemical injection, all that jazz. So I keep them separate. A lot of guys, like you mentioned, a lot of people like to try and tie those together to try and save a control point or a few bucks on a valve.
Well, it did work in the past, yeah, but I'm running into where it's not, but it, you know, you don't have this sock here, so it's on an interval of blowing down itself, right? And
Mhm.
then you get into those shoulder seasons and, you know, just
Oh,
go ahead and 1 inch.
No, it's, I welcome the
It worked
questions,
well.
because it's,
This is all freaking out.
Oh,
so yeah,
All about you.
So you go ahead and ask questions, Susan.
yeah, no, ask away.
But if his phone rings, he's expecting a baby.
Yeah, he's
He's
gone.
trying to be rude.
oh.
He's gone.
Okay.
Yeah, any day now.
Expecting
It
any
is.
second.
So whenever he starts calming down, I send him a text.
Yeah,
Jumps and checks.
my phone's been buzzing here.
Mine's been going off constantly, it's probably.
Peanut gallery.
We're here to help, buddy.
Anything yet?
I'm your number
No.
one fan.
Nothing yet.
Nothing yet?
So here we get down to brass tacks and tell you how this centrifugal separator I've been speaking about actually works. So this is a representation of the filter. Over on the right, we actually can see an example of the filter in black here. Just looks like a solid, a tall black tube. But all of the magic happens on the inside. So we introduce the water at the top of the filter at a tangent. And what that does is actually impart a tangential rotation to that fluid. As that tangential acceleration occurs, it allows the heavier material that's inside your filtration water to get pushed to the outer edges of the filter. And as that happens, gravity just pulls that dirt and material down to the bottom of your cooling tower where it collects, of your filter where it collects. And then through a negative pressure section here at the bottom of the vortex that's created, it actually sucks or pulls the water that's clean up through the center of the filter and out the top. That's an extremely oversimplification of what happens on the inside, as there are a couple steps of acceleration that occur. The first being as the water enters into the filter, and the second that occurs through a set of tangential slots, so it further accelerates the flow and creates that vortex. So if you imagine a tornado plowing through a field and it's pulling stuff up from the bottom, that's basically what happens, but instead of air being pulled around in the vortex, it's the fluid. So that's your condenser water. As that dirt and debris settles down at the bottom, either through an actuated ball valve or, as I mentioned, through a solid recovery vessel, we actually pull that dirt and debris out, and then where we can collect it and then remove it from your system. So the Lakos centrifugal separators are available in a standalone filter. So you can get just the filter itself, where we've installed in numerous applications where there's enough system head pressure to overcome the pressure from the filter itself. And no matter the size of the filter, the pressure range is typically between 3 and 12 psi. That's the flow the pressure drop across the full range of flows that filter can handle. So that filter has no moving parts. There's nothing inside that can wear out. So once the system is set and a pressure differential is reached, typically I like to get it right in the middle in around a 7 or 8 psi differential across the filter. Once that's measured, that can be used as a method to track the efficiency of the filter and the flow rate through the filter. So through an inlet and outlet pressure gauge, you can monitor that pressure drop, and if it does end up either decreasing or increasing, then you know you've got a problem with your system. Either there's something clogging it, you're not getting enough flow, or a valve got open somewhere and now you're increased the flow and it's going out of the bounds of that piece of equipment. So we have a high efficiency model, which is the EHTX. That's anything that you see with the green lettering. That's an oversized Lakos centrifugal separator. And these are sized to filter out 98% of any solids, 44 microns and larger, that have a specific gravity of 2.6 or greater. So that just means any particle that's in there that's 2.5 times heavier than water, it will filter that out the first time through the filter, and it will get 98% of those particles out down to a particle size of 44 microns. And that's about the diameter of a human hair, so it's fine silt and sand. If we go with a standard unit, which is the HTX series on the right, it still operates at a 98% efficient still 98% efficient, but only with solids that are 74 microns and larger. So it requires a bigger particle size. Flow rates will range between 15 and over 12,000 GPM. So in larger applications, such as in the industrial fields, we have units that are 24 to 30 inches in diameter. And if there's any flow rates that are greater than that, we typically just operate them in parallel. Various options for the materials. We could do stainless steel. One option that I've seen in numerous locations in town here is a Scotch coating. So that's an internal coating. They build the filter in 2 or 3 sections, and they coat the inside with, it's a 3M Scotch coat, so that it keeps the material from corroding. So if you have anything that's very abrasive, so we use that in steel mills, somewhere where you get very abrasive material that you're filtering out, that'll keep the internals from wearing out faster. And if high pressure applications are required, we can get CRN or ASME vessels. We've done a few applications in town where we needed to put the filter down in the parquet level, and you've got a 20 to 30 story building with all of that head pressure pushing down on the unit. We've got units that are over 300 PSI operational pressure. So we do require some different certifications for those. So this is a diagram showing how best to plumb in one of your HTX. This is one of the larger systems, but this would operate in a full flow. So we would have the system coming through your typical strainer, through your system pump, and then through the unit and out to whatever is downstream of the unit itself. But this would be 100% flow through our system. And this would once again be a 100% water loss, a zero water loss option, where we're collecting the debris out of the bottom of your filtration system, collecting it in our solid recovery vessel, and then just providing a line for the liquid to escape back to the negative pressure section here. So when this does get full, we can isolate the flow, clean out your filtration sock that's in that solid recovery vessel, and then close it back up and put the filter back in. This is a side stream, so here we're diverting a portion of the flow, and in this type of system, we recommend having it downstream of your system pump, so that we've got a positive pressure to push that liquid down into the filtration unit, and it'll go back up and return to either a cooling tower or back to source, so that you're not losing any fluid. This system here is one of our package systems. It's what we see most commonly used with a cooling tower. This system will come fully assembled. It'll come with a system pump, your centrifugal separator, your solid recovery vessel, as well as your cooling tower control, or your filtration control panel here. So it's essentially a plug-and-play system. You drop it down and wire up your power to that main control panel. It has an HOA switch, so a handoff auto switch on the front, so you can either tie it into your BMS or leave it run. I've seen some buildings where the operator comes in, will turn it on in the morning and turn it off when he leaves, just so he knows that there's not going to be any issues when he's gone. The solid recovery vessel on the side here is plumbed in, so there's no piping required on site. Besides your inlet and your discharge connection to and from either your sweeper or your condenser water. So these systems here, there are a few different models that are available, your high efficiency or your standard efficiency models. And once again, everything is packaged. It comes on a stainless steel skid so that you can just drop them down in your mechanical room and you don't have to worry about it. So the package systems, we can get up to about 3,000 GPM. So in any cooling tower system, because we're sizing 1 GPM per square foot, even on your bigger systems, which have typically a 12 by 24, sometimes a 12 by 36 footprint, you're looking at 360 to 450 GPM. So any of the larger systems, those would be for your industrial size plants or a very large side stream application that you're looking for. So basically have a range of products that'll cover you for any application with fluid flowing through it. So I do have a couple extra slides with some other filters that we have. So this is if you need sub-micron filtration, so anything down to about a 0.35 micron level, which is cleaner than most drinking water. We do have some options for that, but that we rarely see in cooling tower applications, but it is available if you guys do need them. So a little summary for you. Why choose Lakos? There's no maintenance required on the system itself, besides the occasional cleaning of your solid recovery vessel. But inside the filter itself, there's no moving parts. We have 0 water loss option, so once again, as you mentioned, you're not fighting your chemical treatment system. A very small footprint for what you're getting, and typically the filters, they get larger in diameter, but mainly in height, and that's in order to create that vortex that you need in order to filter that material out. So the footprint remains fairly small, just gets a little bit taller for each of the systems. And all of our systems, as they're designed, they get tested by third-party independent testing facilities. So they send their filtration skids off to a third-party lab that's independent. They are tested, and the efficiencies that we provided, so that 98% efficient filtration, is provided by that third-party testing. So it's not a number that's just magically made up to make us look good. It is actually a tested and certified value that we can provide if needed for the owners. So from there, I'll answer any questions that all of you may have. And once our questions are answered, I've got a little demo here that we can run through to show you guys how the filtration system actually works. So if you all want to gather around. So this little gadget actually represents your Lakos centrifugal separator. It is actually a scale model of the filter, and it is actually a fully functional filter. So they do have units that are this small. They're basically made out of, they'd be made out of metal, but this one here is made out of Lexan. Your pump for your system is represented by the small pump here. It's taking water from your cooling tower basin, pulling that dirt and debris up, providing it to the top of the Lakos filter, and it's introduced to the Lakos filter at a tangential angle, where you get your tangential acceleration up at the top of the filter. That water is then pushed through secondary tangential slots in the top of the filter, which accelerates that tangential acceleration. So down in the barrel of the filter here is where all the magic happens. So your dirt and debris, through that centrifugal action, gets pushed out to the outer walls of your Lakos filter. And then from there, gravity will pull it down and it settles down into the bottom reservoir of the Lakos filter. As that water is creating a vortex down the center of your filter barrel, creates a negative pressure section in the center, and it actually, if I introduce a little bit of air into it, sometimes you can see the vortex that's created right in the center. And that's actually pulling the clean fluid that's in the center up through the middle of this filter out to the system discharge. So that clean fluid that's discharged gets sent out this line here, which represents your sweeper piping that's come back into your PVC piping inside your cooling tower, where that clean flow is pushed through a set of nozzles. And that set of nozzles, if they're properly adjusted, will actually push all of the dirt and debris towards your system drain, where it's picked up by your pump, pushed to the filter, and then filtered out.
So why they call it sweeping?
That's why they call it sweeping. So if we were to sit here and leave this for about 10-15 minutes, it would clean up all of this. The black particles in here are zeolite from in a water softener. It would pick up all that zeolite and then deposit it down in here inside the stainless. So, yeah. So that, in a nutshell, is your cooling tower system and how we can filter it and make it run more efficiently.
Have you changed the